Okay, yeah. So in the last class of the statistics, we have learned how to predict a particular mean by getting different samples, right? So that's the last topic which we have discussed. Before that, I mean, after that, we have discussed about the,
Sir,
yeah.
sir, can you increase your voice?
Okay, is it good now?
Yes, sir.
Okay, good. Yeah. So, like yesterday, what we have seen, how to eliminate the outliers as well. Like a simple formula we have seen, that is x minus mu by sigma. Like we have randomly generated some numbers. You remember, right? Like we have randomly generated few numbers, like 5 to 6 data points, and out of the after the 5 to 6 data points, we have added one outlier. Like wantedly, we have added one outlier. That's outlier is something, right? So it's a different number from the group of numbers. Yeah. So in order to eliminate that kind of patterns, that kind of outlier and all, so to make the pattern very valid for the machine and all, so we use certain techniques to eliminate those outliers. Okay, yeah. So one of the technique what we have seen is, that is x minus mu by sigma, where x is the data point, mu is mean, and sigma is the standard deviation there, right? So likewise, we have seen formulas, like we have seen the formulas, right? We have seen different formulas, like we have seen covariance, correlation. These everything will come up in Python actually. Now again, when we start data science and all, I'll tell you how to check the correlation between the data points and all. I'll show you that. But you need to remember the concepts properly, because right, the correlation. So for example, if the correlation is there, so correlation is something where it ranges from -1 to +1. Yeah, we have discussed this. The one is a positive correlation. That means the both the values will move in the same direction, right? So -1 is the negative correlation. That means the values move in the opposite direction, right? So likewise, you need to understand the concepts more. Like practically, you need to think like how you can use the value. I mean, how you can use these statistics in real time, right? Everything, like we have learned probability in our math classes and all. We have learned matrices, right? We have learned eigenvalues and eigenvectors, if you remember, right? So these all are very useful actually. So each and every concept of math has got like a real time, has got a real time approach, right? So while you're learning now, like your teachers are teaching you something, it's not like that. So when the teachers are teaching you something, you ask them the questions like this, like why we use eigenvalues and eigenvectors, kind of. Are you getting my point? Like why we use matrices? So we just simply learn the concepts, and we just simply uh, by heart the things and do it, right? It's not like that. See, if you're using trigonometry, there should be some use, right? So learning that much math, like from the childhood, we are learning so much of math. So that's where, so if you learn the math, like understand the concepts of the math, not the formulas, again I'm telling you, if you understand the concepts of math, data science will be very easy for you. Okay, but understanding that is a little bit complex, remember, because yeah, it's a typical subject again, because it involves a lot of math and all. Yeah, I'm not going to teach you the entire math like involved in the data science and all, because yeah, since that would be like advanced course for you guys. So I'm going to teach you like how we are going to use these things in the by using Python, and how we are going to solve the data science problems. Okay, yeah. So coming to stats again. So till now, we have seen the statistics like mean, mode, median, and inferential statistics, the distributions, probability distributions. Like I've given you two examples of the probability, not much, yeah, but two examples of the probability and all, right? So we have seen standard normal distributions also, and we have used the standard normal distribution formula, right? The x minus mu by sigma. Okay, so there we have finished. Okay, so standard normal distribution. Yeah. Since why we are going for standard normal distribution, in order to make our the entire data points in the form of a normal distribution curve, right? To eliminate the outliers and all, and to make sure that the distribution is normal. Okay, then only the machine will understand perfectly, and we can get good accuracy results. Okay, yeah. Standard normal distribution, it is denoted with Z. Okay, a normal distribution with zero mean and variance one is a standard normal distribution. This thing we have already discussed. So you remember, right? Like first we have calculated the mean of the entire population, I mean the entire values, and then we have applied x minus mu. After applying x minus mu, the mean value has become, has brought down to zero, right? The mean value was zero, and after that, by dividing that by standard deviation, you can call the variance of standard deviation the same, because square or the root something of one is one actually. Okay, So one is a standard normal distribution. Yeah, see, and a mu comma sigma square, the variance. You can use standard deviation also here, that's fine. Mu comma sigma square is, yeah, n of 0 comma 1, like 0 comma, that is the mean would be 0, and sigma, I mean the variance or the standard deviation would be 1. Okay, that means we are not like changing the information, you're getting the point, like you're just reducing the scale. So by reducing the scale, the mean will be minimized, right? So if the mean is minimized, the pattern remains the same, but the mean, we are reducing the mean there. So we are reducing the mean and we are reducing the standard deviation. What happens there is we are changing the entire scale and we are bringing that to the bottom. So instead of having 1000, 1200, 1300 value, we are bringing that to a scale of -1 to 0, 1, or 2, 3, kind of near to 0 and all. So when you bring near like all the data points near to 0, so the distance between the outlier and the other group, no, it becomes so negligible. It's negotiable. It's negotiable. Okay, yeah, sorry, I got a call. Yeah, done. So see, a standardized variable. Okay, a variable whose normal distribution we are turning into a standard normal distribution is called a z-score. Okay, so the formula x minus mu by sigma, x minus mu by sigma, z-score is x minus mu by sigma. That's the formula. Example, take a data set, like yesterday also we have taken the data set, right? So standard normal distribution, see, so this is the standard normal distribution curve. That means it is exactly same as the normal distribution curve, but what we are doing is we are converting the entire mean into 0 and the entire variance into 1. That's the basic difference. Okay, so the standard normal distribution is a particular case of the normal distribution. I told you, like it acts same as a normal distribution curve only, but it has a mean of 0 and a standard deviation of 1. Okay, every normal distribution can be standardized using the standardization formula, right? So can be standardized in the sense, I mean we have reduced everything into a lower scale, right? So that is called a standardization. Like we are setting up a value to the proper value to our entire data set. Actually, we are smoothing the curve, you can tell, something kind of. Okay, anything, like anything, if you're manipulating the data without the loss of information from the data, no, by this is called a standardization. Okay, z is equals to x minus mu by sigma. A variable following the standard normal distribution is denoted with the letter z, the letter z. Yeah, that's right. See, this is the curve and we have this n, that's a normal distribution. But if you have 0 mean and standard deviation, and at the time this n becomes the standard normal distribution. Okay, why we need to standardize? Standardization allows us to compare different normal distributed data sets. See, we can compare different normally distributed data sets there. Detect normality. I mean, like if the normality, if it is present in that or not, and if it is divided equally or not, if it is divided in a normal distributed way or not, kind of. Detect outliers. See, so detection of outliers. So I told you, like yesterday we have seen that example. Like we can detect the outliers, and create confidence intervals. Yeah, still we haven't come to these topics, so we'll leave these topics behind, and once the topics are there, you'll understand. Create confidence intervals, test hypothesis, and perform regression analysis. Okay, yeah, so rationalize to the formula for standardization. So we want to transform a random variable, I mean, like we want to transform a random variable, any variable, from mu comma sigma squared to 0 comma 1. Okay, subtracting the mean from all observations would cause a transformation from, see, this is the thing actually. So now what we are doing is we are converting the entire distribution from mu comma sigma square to 0 comma 1. Okay, how we are doing it? Subtracting the mean from all the observations would cause a transformation from mu comma sigma square to 0 comma sigma square. That's what, like yesterday we have done that x minus mu. I mean the uh, what do we call that? The mean, the mean and the actual values, we have made the difference, and after doing the difference, when we calculate the mean of the data points, the resultant data points, that time we got the value as 0, and but the standard deviation remained the same. Okay, moving the graph to the origin. You see, this is the point, like we are moving the entire graph to the origin. Previously it was not at the origin, like near to scale, near to zero scale, right? Subsequently, dividing all observations by the standard deviation would cause a transformation from n of 0 comma sigma square to n of 0 comma 1. Standardizing the peak and the tails of the graph. See, previously we were not able to like standardize the peak and tails of the graph, but now after doing, I mean, like after getting the data points, after applying that z-score and all, now you are able to standardize the peak and the tails of the graph actually. Okay, yeah, so that's very important. Okay, so till here, yeah, we are good. Like we have done something and we have applied the z-score, and yeah, so after that we have a theorem, that is central limit theorem. Okay, so what it is, this is one of the most important concepts in statistics. Take any data set irrespective of the distributions. See, irrespective of the distributions, I mean, it might be a normal distribution, or it might be a binomial distribution, or it might be some uniform or random distribution as well. Okay, so random distributions we haven't discussed, right? So random distributions are something, if, I mean, randomly, if you create any distribution curve, like different data points and all, so it comes up with a lot of noise, right? Obviously. So if you're applying some random distributions and all, you'll get a noise and all, because you don't know, you don't have that uniformity in the variables, I mean the values. Okay, consider this data set actually. So this central limit theorem, already we have done it. So yesterday, if you remember, like we have taken a set of data points. See, I mean, randomly we have picked some data points, and then see, take samples from the data. Okay, we have taken the samples from the data and calculate the mean for all the samples, no matter the distribution. Again, no matter the distribution, you just calculate the mean for all the samples. Okay, so we are calculating the mean for all the samples here. The means of the sample you took from a data set will approximate a normal distribution. See, the means of the sample you took from a data set will approximate a normal distribution. Okay, that's what, like yesterday we have taken like some samples, right? So first we have calculated the entire population mean, and after that we have calculated the mean for different samples. Like we have taken 4 samples and we have calculated it. Okay, the more samples you extract, the bigger they are and closer to the normal distribution that sample means will be. That's the point, right? Yesterday we have taken 4 samples, and we have approximated by using we have approximated the population mean by using these samples actually, right? So now the normal distribution will, I mean, the closer we get closer to our normal distribution if you take more samples. That means the more samples you extracting in the sense like keeping it aside, like group it and keep it aside and do something. Like yesterday we have taken from 0 to 21 sample set, 20 to 40 other sample set, 40 to 60 other sample set, and 60 to 80 other sample set, and in between we have taken like randomly 7 to 27 or something. That's a different sample set again. Like we have likewise we have taken like 4 to 5, I guess, I don't know. So but yeah, 4, I guess we have taken 4. Likewise, you, the more the samples you extract, the bigger they are and closer to your normal distribution, and that's how you can approximate the population mean actually. Okay, now you are getting my point, right? At first we have started the statistics with the definitions of population and sample. Remember, I have given few examples of population sample as well, like the job prospects. Like for I mean, if you want to know about the job of how many students are placed in a particular college and all, it's obvious, right? If you go to each and every student, it's very difficult for us. So statistics will be useful there. You take samples from the data set, and we try to approximate that value, and the samples is a representation of the entire population actually. Okay, clear? Yeah, so now you are, I guess I hope everything is clear now, because so when we started with the definitions of population sample, yeah, like I told you, like why samples are important, I'll tell you in the later classes, right? Now you understood now. So taking samples and doing it with, see, yesterday we have taken like only 100 data points. What if you have 1 million data points? Can you imagine, right? So what if you have 1 million data points and you want to find the patterns from the data? Then it's very difficult for us, right? Yeah, yeah. So for that sake, we consider samples. So when we enter into the data science world, so there also, we train the machine with the different samples actually. Okay, so train the machine with samples actually, not the entire population and all. We divide the data sets into some sample data set and we do it. Okay, yeah. Yeah, you understood, right? Why samples are important? Because sample, if you do it, the time consumption is low, and financial. If you look into financial process, also it takes less cost compared to the population, because population involves like so many data points, so we need to like utilize more resources. But sample, I mean, we take samples, right? Small samples we take, and yeah, the resources also will not be wasted that much. Okay, so no matter the distribution, this is it. No matter the distribution. Now the normal distribution curve. This is a central theorem formula actually, central limit theorem formula. So no matter the distribution curve. So these are the like, see, random distribution. Can you see the fourth one? Fourth one, it's a random distribution completely. As you can see, there's a zigzag kind of lines on the graph. That means, so there's a lot of noise with the random distribution and all. It's very difficult for us. So at that time, now we can standardize our data set by using the central limit theorem. I mean, not standardize actually. So like, sorry, I got confused. So when you approximate the values and all by using this, by extracting more samples, you can do it. Okay, check this out. Check this out. See, so now the normal distribution curve, the formula has changed now. So the normal distributed, it belongs to now mu comma sigma square by n. So because we are extracting the samples now, right? Small n represents the samples, if you remember. So for that sake, the number of samples, how many you are taking, there you will be adding that. Okay, so the more samples you extract, the k value, the constant of the k value goes to infinity, the bigger the samples. Okay, that would be a good accuracy for you. The more the samples you extract, the more the patterns you will get it from the samples, which represent the entire population, and you can approximate the actual mean with that. Okay, standard error. See, so this sigma square by n, so standard, it is a standard deviation formed by all the sample means. Okay, it is standard deviation formed by all the sample means. Okay, the formula for that is standard error is equals to square root of sigma square by n, that is equal to sigma by root n. So this is the formula actually. So yeah, so we'll see why standard error. Okay, it shows us how much we approximated the true mean, right? Yeah, so yesterday we have done something, right? Standard error, it shows us the how much we have approximated the true mean. Standard error decreases when sample size increases, gives us a better approximation. Yeah, which is, see, if the standard error is decreasing, that means the accuracy is increasing, right? It's natural, right? Whenever you decrease the error rate in any problem, our success rate will increase automatically. Our accuracy rate will increase, right? Same goes the reverse way also. Like if the standard error is increasing, the sample size, when sample size decreases, gives that doesn't give us a good approximation. So when the sample size increasing, you're getting a good approximation, that makes the standard error decrease. Clear? Yeah, I guess it's clear. So yeah, so this thing we already seen it, and now here you can see the central limit theorem actually. See, central limit theorem, it says that no matter the this thing, yeah, I'll share this PPT, just have a look at it. It's the same thing. Whatever we are discussing now, it's the same thing actually. See, why is it useful? See, the more samples, the closer to normal. The bigger the samples, the closer to normal. It's the same thing. Sample size, if you increase, you get close to the normality. If you increase the samples, at least sample size and samples are different. Increasing the number of samples, also you'll be closer to the normality actually. Okay, so why is it useful? The CLT, okay, the central limit theorem allows us to assume normality for many different variables. So that's the point, right? We are using everything to get it down to the normality. That is very
Sir,
useful for confidence. Yeah, please.
sir, for bigger sample, the closer to normal, sir. How it, sir? Can you explain, sir, once?
Okay, sure. Yeah, so yesterday we have taken samples of 20, if you remember. Sample size each, I mean, we have taken 4 samples and each sample size was 20. Okay, what if you increase the sample size, increase it to 30? See, you'll be approximated to the true mean, right? You'll be close to the true mean, because the more the number of samples, okay, but the size of the sample, size of each sample, the data points present in each sample, if you increase them also, obviously now if the data points are getting increased a little bit, that means, so we are getting a good pattern from the data, kind of like the more the amount of data, the more the patterns will get it. Okay, yeah, so why is it useful? Yeah, we are discussing this. The CLT, allows us to assume normality for many different variables. That is very useful for confidence. Okay, we haven't started the confidence intervals and also leave it. Hypothesis testing and regression analysis. Okay. In fact, normal distribution is so predominantly observed around us due to the fact that following the CLT, many variables converge to normal. Uh, yeah. So see anything like if you're doing something with the central limit theorem and all, no, ultimately like you see. So this is the point. Can you see the graph here? Can you see the graph here? This graph is being converted into this normal distribution. See, central limit. That means you, in a way you're standardizing the things as well. Like, yeah. So the main point is you need to convert the entire data points into proper normal distributed curve. Okay. So that means after converting that into a proper normal distributed curve, no, the patterns, whatever are they present in the data points, will be effectively noticed by the machines, by the algorithms and all. And with the patterns, we train the machine, and that's how the pattern training goes on. Okay. See, yeah. 1 minute, I'm getting a call. Yeah, sorry, I got a call. Yeah. So we are where we are. Yeah, we are at central limit theorem. See. Yeah. Okay. So the central limit theorem, as we have discussed about the standard error and all. So remember, the error rate will be everywhere. So when we start any machine learning algorithm or anything, if you are approximating something, error rate will be common everywhere. So the main intention for us to be, we need to reduce the error rate as much as possible, right? Yeah. Okay. After this, yeah. So let's go with the next slide. That is estimators. Okay. The next concept is estimators. Okay. Okay. So it is an approximation solely on sample information. See the again. So we are doing that approximation only. So we are talking about the approximations only a lot, right? The value we obtain after approximation is the estimate, right? That's not the true value, right? So it's an estimate what we are doing it. Right? So whenever you're doing some approximations on sample information, the value that you're getting out from that sample information is the estimate. Is the estimate. Like that, how many types of estimates are there? Let us see. The first one is point estimate. The second one is confidence interval estimates. Okay. Yeah. See, point estimates are like a single number. Single number. Like how we got it. How we got it. Right? Like how we have approximated the true mean. Like if the true mean is 570 something, we got the value as 475. So that's a single number. So single number is called as point estimate. Okay. And confidence interval estimates, as it is clearly, you can see it. Like it's an interval. It's an interval actually. So we assume that if you do the confidence interval for that entire population mean, then we assume that the value is lies between 475 to 550, for example, 550, right? So 1 minute, guys, I'm getting a call again. Okay, I'll silent it. Okay, yeah. So that means you're assuming, like you're estimating in the form of an interval now. So previously you're doing it with the kind of point estimate and all. Now you're assuming and you're defining it in an interval, the entire point estimate. Sorry, I mean in an interval, the entire the actual value, you're defining it in the form of a interval. See, point estimates is a single number. Confidence intervals is usually an interval. These two are closely related. How? The point estimator is located exactly in the middle of confidence interval. See, confidence intervals provide much more information when making inferences. Like while making inferences, in the sense if you're collecting some insights from the data, or if you want to come into conclusions out of that and all, no? At that time, confidence intervals are very useful. Okay, so if you have a point estimate, that means in between the interval, you'll have that point estimate. Okay, point estimators, we have already seen these estimates actually. So x bar of mu, this thing, the mean, the estimator mean, the sample mean of the entire population mean. So suppose something, some result is there. So that result is called as estimate actually. The same goes for standard deviation and the variance. Variance is here, and we can you can go for standard deviation as well. That's fine. Okay, yeah. So it has got two properties. The estimators has got two properties. One is the bias. The second one is efficiency. Okay, what is this bias? An unbiased estimator has an expected value equal to the population parameter. Okay, that means x bar is estimated to mu. So we are doing something right there. So the unbiased estimator is something expected value, which I mean, like we are not like we are approximating it. So whatever we have done is the biasing thing. The efficiency. The most efficient estimator is the unbiased estimated small variance. Okay, if you have a small variance and your estimation to the population mean, like you got a value and you have a small variance of all the samples, then that time it will be very efficient model. It's an efficient model actually. Okay, it's an efficient model for what? It's an efficient model for calculating the actual mean actually, I mean, from the samples. Okay, see, so point estimates are not very reliable because it's a point estimate. It's a single point. We don't know. Right? Why again? Why confidence intervals are more reliable than point estimates? So I have a question. I've given you an example here. Considered like, okay, so see you want to go to a restaurant and think like this. So the cost of biryani, the average price, of 5% of restaurants in Hyderabad, and Hyderabad is like 125. The biryani is 125, for example. Okay, that the biryani has got a range, the price range, not range, has got a price of 125, and you assume that okay, the biryani, if I go to any restaurant, like after checking out the sample sizes, the different restaurants and all, the biryani price was 125. So you assume that the price is 125. So you want to try in a different restaurant now. So if you're going into a different restaurant with this 125 rupees, what is the possibility that you'll come out from the restaurant by paying the bill of 125? We don't know, right? So at that time, no, we need to think of confidence intervals. Remember, we may be close, but the chances are like the true value is not 125 bucks. Okay, it might increase from 100 to 150. It might be like less than 125 also, we don't know, but greater than 125 also, we don't know. Then what you'll do, the maximum price you'll take it, you'll put in your pocket, right? The 150 rupees, right? Yeah, confidence intervals are much more accurate representation of reality. That's the point. Like based upon the point estimate, you can't it's not that reliable because see, 475 is the mean you have got. 527 was the actual mean. So that's not good. If you do that in a confidence interval level, like if you say that from this range to this range, the actual mean is, the time confidence intervals are more reliable compared to, like, at least we can assume that the actual mean is present in between these intervals. At least we can have some close approximation, right? Yeah, see, still there is uncertainty. Yeah, definitely, still there would be one uncertainty. We are not 100% sure whether the price is in between 100 to 150. That's true. So still also we don't know. The price might increase or decrease from 100 also, we don't know. Hence we go for level of confidence. Okay, so we have this level of confidence, and it is denoted by 1 minus alpha. 1 minus alpha. Alpha is a value between 0 and 1. Okay, check this. So this is a confidence level we have. For example, if we have 95%, then alpha value will be 5% actually. 5%. Okay, and if you have 99% of confidence level with you, then the alpha level will be 1%. Okay, the alpha level will be 1%. Okay, see the point estimate, if it is in between, so how to calculate the confidence intervals? Obviously, like if you have confidence intervals, then definitely you can have the point estimate in between. But what happens if the confidence level is at 95% only? Then how come you are going to calculate the variation? So if it is 95%, if you're 95% confidence level, then 100 to 150 is not the range. It might increase or decrease also. We don't know. So at that time, now we use this standard error and reliability factor, and we do that for point estimate, and we come up with the uh, confidence intervals. Are you getting my point? See, point estimate minus reliability factor into standard error. That means, check this, minus reliability factor into sigma by root n. This is the formula. Sigma, standard error is sigma by root n, right? Yeah. So it is, okay, confidence intervals. It is the range with which you expect the population parameter to be. We can calculate confidence intervals in two main situations. When population is known, when variance is unknown. I mean, the variance of the population is known and the variance is unknown. So we use different calculation methods depending on above two. Okay, depending upon the two, no, we use different methods actually. Okay, let me check this. Okay, see this. So estimators and estimates. See, estimators, broadly, an estimator is a mathematical function that approximates a population parameter depending only on sample information. So depending on the sample information, we do it. So estimator is x bar here, x bar, s square, and correlation factor, rho, whatever it is, mu, sigma square, and rho here, r and rho, yeah. So correlations and all. So these are the estimators actually. Okay, bias and efficiency, this thing I have told you. Yeah, we'll just, you can have a look at it. Estimates. An estimate is the output that you get from the estimator, right? That you're getting out from the estimator, the output, whatever you're getting is an estimate. So these are the two different estimates here, point estimates and confidence intervals. Examples we have are much more precise than point estimates. This is why, that is why they're preferred when making inferences. Okay, check this out. Confidence intervals and the margin of error. Okay, the reliability. Okay, so the margin of error, ME is nothing but reliability factor into your standard error. That is sigma by root n. That is sigma by root n. So definition: a confidence interval is an interval. Yeah, so we already know the definition. We build the confidence interval around the point estimate. Yeah, we don't know like when.
Sir,
Yeah,
sir, estimates is a output of estimator, sir.
yeah.
Means a sample output, sir.
Okay,
Yeah.
sample mean is estimated. So if you are calculating some output out of the sample means, like maybe if the sample mean is your entire output, then that sample mean would be the estimate. But what if you have 4 sample means there? So those are the estimators, and out of 4 you are again calculating a mean. That is an estimate for the population. Okay.
Okay, sir.
Yeah. So I'll show you a practical example. Like tomorrow, tomorrow we have class at the same time. Till then, I'll just share the PPT with you. Have a look at this PPT and all. Okay. Till here we are good.
Yes.
Like we are good. I mean, like we know how to calculate and all. I'll show you a practical example. Okay. Yeah. Okay. Fine then. So let's catch up tomorrow. So we are done with the class for today.
Sir, we have a class on tomorrow, sir.
Yeah.